Hello everyone, my name is Amélie Gruel. I'm a third-year PhD student at Alfio at CNRS, and today I will be presenting our work on embedded neuromorphic attention model leveraging a novel low-power heterogeneous platform. This work has been performed in collaboration with my supervisor, Jean Martinet, and student postdoc and researchers at IEEE Zürich in Switzerland, which are Alfio, Hunziker², Luca, Benini², and Michele Magno². We are going to talk about different neuromorphic materials, so I'm just going to present you both of those that we are going to use in this presentation. The first one is event camera. This is a new kind of visual sensor that is bio-inspired, and unlike traditional RGB camera that records RGB data at each pixel with a certain interval of frames, event-based camera will record at each pixel short activation, just on-off activation, if and only if there is a change of luminosity at the corresponding pixel. This produces really sparse data that is totally asynchronous, so that requires only a low memory and also a low power consumption to be produced. This innovative kind of data is specifically suited to be used and processed by spiking neural network. This type of artificial neural network is bio-inspired, and unlike traditional neural network, it uses trains of spikes to translate information and the data instead of floating point numbers. The spiking neural network is low power, especially when it is implemented on neuromorphic hardware, which is a hardware specifically dedicated to running this kind of neural network at a low power consumption. This spiking neural networks combined with event-based camera, both interfaced and implemented on the neuromorphic hardware, are the perfect combination to be embedded on a drone, for example, because of their low power consumption and their low need of memory. The specific neuromorphic hardware that we are going to use in this work is Kraken. So Kraken is an academic platform that has been implemented in 2022 by Alfio and collaborators. It is a low-power, RISC-V-based system-on-chip prototype, including a neuromorphic spiking neural network accelerator. All in all, using this Kraken platform, we are going to implement a reference model. Our reference model that we choose is an existing architecture that we implemented and submitted at AICAS 2022 that allows for the detection of visual attention in event-based data using a spiking neural network. What is visual attention? It is a behavioral and cognitive process of selectively focusing on a discrete aspect of sensory cues. This model is quite simple, as you can see. It has only 3 layers and is connected using only 2 types of synaptic connections, and the whole mechanisms is allowed by 2 adaptation rules. The first one is a weight adaptation rule that is between the input layer and the saliency detector. This weight adaptation rule will increase the influence of events that are in the region where there's a lot of events in a short amount of time to be taken into account by the saliency detector, and vice versa. It will decrease influence on the saliency detector of sparse events in the input data. Additionally, we have a second rule, the threshold adaptation rule, which is more innovative, even more. According to these threshold adaptation rules, the regions that were detected in saliency detector will see their corresponding neurons in the output layer have their threshold decrease in order to facilitate the passing through of events. And a contrario, we will have the neurons in the regions that were not detected as salient by the saliency detector see their threshold increase in order to inhibit the activity. This model was initially implemented using a CPU simulator, which is Pine, and LOI in our previous paper of 2022. And now we are going to implement this model on PyTorch, which is the framework that is used to implement spiking neural network on Kraken. In order to do so, we have to do 2 steps. First, we have to update the parameters, because Pine uses really bio-inspired parameters, values, while PyTorch does not. It uses more floating values, positive always. And the second thing, more interesting, is actually to modify the connection, because on Pine we were able to implement connection between different layers. On PyTorch, we had to implement, for example, the input to silencer detector connection and the input to output connection as linear and convolutional layers in order to implement this reference model on Kraken. With all those modifications and all the information that I just gave you, we were now able to run our model on the Kraken platform. We use the dataset DVS 138 gesture in order to validate this model and this implementation. This dataset is a commonly used dataset, so it is an event-based one, where different people came and performed different type of hand gesture, specifically 11 different hand gestures, in front of a DVS 138 camera. In total, we have around 133 samples available for each gesture, and one sample is roughly 400,000 events that last during 6 seconds. We apply our visual attention model to this data, assuming that the salient element that it is going to detect in this data are the movement done by the hand. So after the selection by this model, the events that are output by the model will correspond only to the hands of the person performing some gestures. And these hands will be enough in order to classify the between different hand gestures and thus obtain a qualitative result. Here we have a presentation of our experimental results while comparing between CPU implementation, the LOE implementation, and the Kraken implementation, which is the current one. If we take a look at the simulation time on CPU, in order to process 1 second of input data, we had to use 3 seconds of real time to process this efficiently. This is due to the fact that CPU are not well suited to simulate spiking neural network. It is just hardware limitation. However, on LOE, that is more adapted to that, we managed to reach the simulation time of 6 seconds, which is way better. But on Kraken, we managed to outperform real time. So in 10 times less than in real time, we managed to process 1 second, which is a good result for us. This is the time it took in terms of time step to detect an object of interest in the scene, so a salient object in the scene, and to select it and to output it. For CPU simulation, we managed to do that in the equivalent of 5 milliseconds, which is quite quick, even knowing that the event data is recording at the time grain of microseconds. A millisecond is a good enough amount for us. On LOE, we managed to reach this with only 20 milliseconds, so not as good as on CPU. And finally, on Kraken, we managed to reach the decision with an average of 32 milliseconds. This is explained by the fact that the data that we have, so the DVS 100 gesture dataset that we have, was processed in such a way that the events were accumulated into frames of 15 milliseconds. So it took 32 milliseconds to detect an object of interest, but actually it took only 2 time steps. This is a limitation that is due to the hardware itself, so in later results you are going to try to run this neuromorphic model implemented on Kraken on a new data that doesn't have those limitations. Finally, we took a look at the classification accuracy. We used a classifier that was adapted to classifying between the different hand gesture in DVS 138 gesture, and we gave it the output produced by our neural network when implemented on CPU and on Kraken. Sadly, we do not have this data for LOE because our collaborators have left the lab. We can still compare between the CPU implementation and the Kraken implementation. On CPU, with the events that are output by our model, we managed to reach a classification accuracy of 67%, which is good enough, knowing that we have 11 gestures to classify between. However, with Kraken, we managed to reach a good accuracy of 85%. This is explainable, this difference in accuracy is explainable by the fact that knowing that we have the preprocessed dataset where the events are accumulated into frames, so activations that are produced by those events are more dense than on the CPU. If there are more events, then it is easier to classify, especially for the classifier that we use. So this might explain this high accuracy level. Now we can take a look at the latency and energy consumption details of the silencer detection model implemented on Kraken. So as you can see here, the energy consumed and the latency in seconds is detailed in between the different layers, so between the layer input to rate detector, winner take all on rate detector, input to output, and winner take all on output. And we can see that all in all, this model required only 3.85 millijoule to be processed. And as I told you earlier, it needed only 0.14 seconds to be processed. All in all, we have managed to implement an existing model of visual attention on Kraken with only the consumption of 3.85 millijoule per second of processed data and reaching a 85% accuracy in the classification task on the selected objects. We have managed to process the data 10 times faster than real time, and we are happy to say that this is the first conclusive saliency detection algorithm deployed on Kraken. You can see on the left the hardware that we used in order to produce the data. And finally, I can let you know that your future work includes maybe comparing the energy consumption that we recorded on Kraken to the one that we might record on CPU and on LOI using the same model. And finally, we wish to implement this reference model on Spinnaker in order to complete our comparison between neuromorphic hardware. Thank you for your attention. Do you have any question?